All right, everyone, welcome back. We're doing. Ooh, Kitty just tried to fight me. Ooh, oh, I need lights. I am not ready. I'm not lying here. Donkashay, darling. Welcome back. We're picking up with some more recursion practice. This is going to feel an awful lot like yesterday, and that's fine. I got some stuff coming down the pipeline. I need to make sure that all y'all have IntelliJ installed if you really want to participate and get the most out of what's coming up in the coming days. Let me get a thumbs up in chat if you have IntelliJ ready to go. In the meantime, recursion. Yesterday when we left off, right, we're doing count 8. Let's pull that bad boy up. Coding bat. And plop plop. All right, count 8. Given a string, that's not count 8, that's a misclick. Count 8. Given a non-negative integer n, compute recursively. I like how they keep emphasizing this in the recursion 1 section because, you know, there's some kids out there, it's just like, I'm just going to do loops. Compute recursively the count of the occurrences of 8 as a digit, except given 8 with another 8 immediately to its left, that counts double. Right? So we're going to get some type of integer. If we want to know how many times does 8 occur, we see that in the event that we actually have back-to-back 8s, that's actually going to yield us 4 instead of the normal 1. So they have a reminder here that mod 10 will give us the rightmost digit. If I were to take 126 and mod by 10, I'll get the rightmost digit, which is a 6, while divide by 10 removes the rightmost digit. Exact same number, divided by 10 effectively chops it off. So let's get into this. We're going to kind of power through this because I've already gotten a lot of solutions, which were really good, some real clever stuff. For instance, if we just take this number n and we just keep dividing by 10, eventually it's going to reach 0. So that's how we are approaching the base case. With that in mind, a potential base case is just literal 0. If it's 0, we can return either 0 or n, doesn't matter. Okay, so that's one base case that stops us when all else fails. Now, another scenario is that the rightmost digit is an 8, but there's only one 8. Other scenarios include the rightmost digit is not an 8, and anyway, there's lots of base cases you can kind of tack on here. What we're most interested in is the rightmost digit an 8. So as we kind of talked about earlier, we're going to use mod 10 to get the rightmost digit of our integer n. And if that number is exactly an 8, I know that the rightmost digit is an 8. So here is where things start to get interesting. Right? If it is an 8, we also need to check to see, is the one next to it an 8? All right, so this is going to get interesting because we've already determined that the rightmost digit is an 8. We need to basically chop off that rightmost digit, right? I just considered this. I just considered the rightmost digit. I want to get rid of it now. And then we're going to take that, right? So now n is slightly smaller, and I want to see, is that equal to an 8? So I get rid of the rightmost digit. Notice that I'm not actually modifying n, right? I'm not actually saving this back into n. So this is just momentarily some math. I don't want you to think that I'm modifying n, even though we're constantly talking about removing the rightmost digit. There's no assignment operator here, so we're not saving it back into n. So I chop off the rightmost digit. I then am going to basically ask, what is the rightmost digit of that number? If that is an 8, what this means is, well, the rightmost digit was an 8, the one next to it was an 8, and so this is our scenario where we're actually returning 4. We'll return 4, but we're also going to keep going, right? Because we're actually counting, that's how I know we're doing addition. And here, I need to approach this base case, right? Having a base case is not enough. We actually have to trend towards it, but we're going to have our recursive call. And we're going to take in and chop off the rightmost digit. Now, this is Yeah, we're going to chop off the rightmost digit and continue on. Okay, now there's a little bit more to this because I have verified that the rightmost digit is an 8. We then check, is the one next to it also an 8? But what if it's not? What if this is false? Well, we're going to have a scenario. I'm going to have to bring in some braces here so we got more than one statement. I'm inside this if statement, so we know that the rightmost digit is an 8. Is it 2? I see what you're saying. Appreciate you. Thank you. I verified that the rightmost digit is an 8. I verified that the one next to it is not an 8. This is the scenario where we return 1 plus, and again, we're going to keep going. Okay. Now, I believe this is going to handle most of our cases. Not quite everything. Help me out, chat. Right? Missing return statement, right? If this is false, this is false, this is false, we're not returning anything. Last one. What if this is false, this is false, this is false? What it means is the rightmost digit is just simply not an 8, but we need to keep going. And the way we're going to keep going is by taking our count 8, putting a recursive call in the stack, but I'm effectively doing 0 plus. We don't have to actually put that there. You can if that mentally helps you out, but we need to basically keep it going. And here we go. So we'll come back to this base case, but simply put, I'm going to ask, is the rightmost digit an 8? If it is, I'm going to check the one next to it. And the way I'm going to do that is shave off the rightmost digit, then check the rightmost digit. If that is an 8, we're going to add 2 and keep going. But if the rightmost digit is an 8 and the one next to it is not an 8, we're actually going to just add 1 and keep going. If I manage to hit this return statement, it means that this was false, and of course this was false. But the rightmost digit basically is not an 8. We just need to keep going, effectively adding nothing. Okay? Eventually, right, this n divided by 10, it's going to keep making our integer n smaller and smaller and smaller. Eventually, it'll hit 0. And that's when we can effectively stop. Now, I'm going to look at some little quirky things here. Right? I did see some solutions. Like, I'm doing this thing here to ask, is the right 2 digits? Like, this if statement combined with this if statement is asking, is the right 2 digits 88? Well, we can actually get the right 2 digits. And I hope some of you can make this leap in understanding. We've talked about a lot how mod 10 gets the rightmost digit. Well, we can actually get the right 2 digits. If I take my number and mod it by 100, what I'm getting is the 2 digits on the right. I want to know, is that exactly 88? That's going to help me drastically reduce some of this stuff. Because I can just do that. Okay? And the order here does matter a little bit, right? I'm checking the right 2 digits to see if we have 88. Then, if I'm still here, what that means is I know that the right 2 digits are not 88, but I still need to check to see, is the rightmost digit an 8? I really like the way this looks. This ends up looking a lot cleaner by using this tactic to get the right 2 digits instead of just the right one. What do we think? Kind of baller. One last little small thing. I didn't see anyone do this. I just wanted to show it to you that you can. Maybe what we do is actually create an integer that represents this count. What I would like you to recognize is that in all 3 of these scenarios, I ultimately am putting a recursive call stack, or a recursive call back onto the stack. The only thing that's changing in these scenarios is this integer, right? So we can actually come in with some integer. Let's just call it x. And what's actually happening in these methods, maybe, is that we're changing the value that's here. Now, I would have to change this order a little bit. Is the cat coughing? Not yet. So if the rightmost digit is an 8, then maybe I set x to a 1. If the right two digits are 88, I'm going to change x. Maybe x is actually 2. Then at the very end, I can return x plus whatever it is here. So in theory, x starts out at 0. But we're going to check the rightmost digit. If it's an 8, we change it to a 1. We then need to make this check to see, well, maybe the right two digits are actually 88, so we change it to a 2. Whatever the value of x is here, it gets added in, and ooh, I'm so glad that worked on the first try. So this is kind of a tactic that you can use. Most students don't do it in practice, to be honest. I just kind of like you to be aware of it because it's recognizing, we're effectively reducing duplicate code because effectively all of these calls had a recursive call associated with them, and it felt an awful lot like duplicate code. So this is a route that we can take. Notice I don't even establish x until I've passed my base case because there's really no reason to. Sweet. Let's go to the next one. powerN. All right, this one's pretty fast, but I like what we're doing here. We're actually, we are, it's too fast. We're actually doing something useful here. We're doing an exponent, but we're actually doing it recursively, no loops. So they're going to give you some base and some power, right? Just a quick reminder, what we're talking about here with exponents is, let me make this thick. Give me a thick boy, right? 3 squared is really 3 times 3, right? And something like 4 cubed is really 4 times 4 times 4. So the only reason why I'm even showing you this, right, this obvious exponent thing that you guys are in like absurd math, I'm sure you get this, but what I want you to kind of recognize that the base isn't changing whenever we do this. You can think about each one of these as a recursive call, and notice the base doesn't change. What is changing is effectively my exponent. Okay, so because we're using that exponent to effectively count down, right? Initially, this is 3, and then 2. I got 2 remaining, and then 1 remaining, that sort of thing. So help me out here. What does our base case look like? Thank you. If n is 0, if n is less than 1, n is equal to 1. All right, we'll see. Let's talk about it. Okay, we have recognized that n is what's going to be changing. The base we're going to kind of leave alone. What that means is that n should get smaller and smaller and smaller. Our base case should be in relation to the exponent here, n. So one thing to recognize is if I have any power or any base raised to the power of 1, that's just the number itself. If I have anything raised to the 0 power, that's literally 1. So you can look at these as 2 separate base cases. Some of you may recognize that you only need one of them. We're actually going to maybe talk about what if n is 0. If n is 0, right, my exponent is 0, that number comes out to be just 1. So you can write this as, if our exponent is nothing, is at 0, we can just return 1. And that could be a base case. Okay? Otherwise, what we're doing is we're going to return the base, right? Our base times, and then here's our recursive call. Same base, that's not changing. What is changing is that n is getting smaller. So we're not modifying our base. Notice it's staying the same. But n is getting smaller. It's going to approach this. And they do tell us that both are 1 or more. So here's a possible solution. Right. With our recursive call, our exponent, n, is getting smaller and smaller and smaller. Eventually, it's going to be 0, as long as it's not a negative number. what we're doing with each iteration, each recursive call, we're taking our base and multiplying it by itself. And now each one of these recursive calls is putting another base onto the stack. Why don't we trace this? So let's say that we're doing powerN. I'm going to abbreviate it just to P. And let's say that we want like 4 to the 3rd power. Okay. First thing I'm going to ask, is in my exponent a 3 or a 0? It is not. So we hit our recursive step where we're going to take our base, which is 4, and we're going to multiply it. We see a recursive call here. So we're going to put that onto the stack. We got same base, that's not changing, but my n value is getting smaller. Well, here I've got a bit of code that's waiting to be executed. I don't know what the value of p4, 2 is. So I'm going to step inside that and we're going to ask, is n equal to 0? It's not. So we hit our recursive step where we'll take our base, which is 4 still, multiply it times p to the 4, 1. Right? Our base is staying the same. Our exponent's getting smaller. Let's step inside this call. We're going to ask, is n equal to 0? It's not. So we're going to hit our recursive call where we take our base, which is still 4, times p to the 4, 0. We'll step inside that call. We'll ask, is the base equal to 0? It is in this case. So in that case, we just return a 1. I'm going somewhere with this, I promise. So now I can solve this. I'm going to replace this with a 1. I now know the value of this. I'm going to replace this with a 4. I know the value of this. We're going to replace this with 16. And I know the value of this, 4 times 4 times 16. I'm totally not doing it. 64. My accountant just botched the math too. So that's how we get our solution of 64. Now the whole point of this, I'm going to back this up. Is there not multiple undo? Yikes. Yeah, just keep going. Oh, Notepad, you're letting me down. There was a step there towards the end where we just have a value of 1 and then we just multiply it by our base, and that's obviously just going to give us our base all over again. The reason why I'm even mentioning this is that's an extra recursive call that's just not necessary. We can make this more efficient by saying that the moment that n is equal to 1, right, we can return n. Now, there's going to be a slight problem if n were to be 0, but they actually tell us that we're given 1 or more. ¿Cómo se llama? No, not n, the base. Right? Once n equals 1, we can actually stop there. They actually tell us that both are going to be 1 or more. Now, the only potential problem, which doesn't actually exist in this coding bat, is what if they give us an exponent of 0? Then we're not actually handling that. We would get infinite recursion because we would ask, is the base equal to 1? Well, no. When n is 0, it's not equal to 1. Okay, let's make it smaller. Right? So that would give us infinite recursion, but in this particular problem, they're not testing for that. And so we can actually stop the moment that our exponent is 1. All right, let's try that with a lot less hiccups on the next one. These are delicious. Given a string, compute recursively the number of lowercase x's that are in the string. So this is our first problem. We've been working a lot with integers, which lead to mod 10, divide 10, but we actually have a string coming in, and I need to basically loop through this string, but without loops. It's going to feel kind of similar to the integer problems that we've been working on, where you're really considering like one character at a time, and then you got to chop it off. You got to get rid of it. Okay, so hopefully there's some buzzwords that are popping off in your head. How do we get rid of characters from a string? How do we access characters from a string? Those type of things need to be happening. So our goal is that we're going to take some type of string and I want to know how many times does lowercase x appear. Okay, so we're going to consider one character at a time, and then once I've considered it, I'm going to get rid of it. Substring, that's right. Okay, if I keep getting rid of characters, when do we stop? What's my base case look like? I see some division here, right? If our length is 0, then I'm out of characters. If I am, if my length is 1, then there's only one character to consider. So it's going to feel very similar to the last coding back that we just did, that maybe we stop when we have nothing left. Maybe we stop when there's actually only one thing left. This is where recursion can get kind of interesting. I see a recommendation of index of. How do you think index of is written? What does index of do? Index of is just going to use a loop to actually go through the string. Of course you like index of. We all like index of. Okay, so let's start with, if we just keep chopping off characters, eventually we have nothing. How do I know? There's a couple of different ways to check to see if your string has nothing in it. We can ask, is the length equal to 0? We can ask, does the string equal nothing? Right? Lastly, one that we don't know, but there is a string is empty. That method exists. I'm going to stick with length is equal to 0, because this is probably the route that most people would go. So if our string has nothing in it, right, that means it is just that. Well, we can either return the string as it exists, because it's just this, or we can just return, we're returning, sorry, a count, an integer. We'll return 0, like an adult. Okay, I'll leave our comment there. It's beautiful. So we're going to consider one character at a time, and then once we've considered it, we're going to get rid of it, which means our string is going to get smaller and smaller and smaller. Eventually, it doesn't have anything in it. So now, so that dictates my base case in a lot of ways. So now I want to basically check a character. Okay, in a lot of ways, it doesn't matter in this case if we check at the beginning or if we check at the end. But some things to keep in mind is, how will you check the one at the beginning? How will you check the one at the end? And as it turns out, it's easier to basically check from the beginning and get rid of off the beginning. It's just literally less things to type. So help me out in chat. Give me a couple of ways that you can actually get the first character from a string. Good. So based on the subset, right, it's substring. Right? Based on what the College Board wants you to know, we can use substring to get the first character. This will give me the first character as a string. And then I would want to know, does that equal X? Notice that we are comparing a string to a string. I'm using a string literal here, using the equals method. That's messy. I'm a big fan of char app, something that's not in the subset, but is a lot cleaner. This is going to get a character, just one, at a particular index. Now, because this is returning a char, I want to compare it using an equals relational operator. We're working with a primitive data type here. And I need to be careful, make sure I use a char literal, that is single quotes, as opposed to a string literal, the double quotes. So we're going to ask, is the first character an X? If it is, I found an X. So I'm going to return 1, and we're effectively counting, so we're going to add, plus, and I need to keep going. So this is where we hit our recursive step. I want you to help me get rid of the first character. At this point, I've considered the first character. I now need to get rid of it in our subsequent recursive calls. Oh, love it. I love both answers I got here. So we're going to take str, and we're going to do a substring. Okay? We can basically start at index 1. Don't forget that our indices are starting at 0, right? I just consider the character at 0. I don't want to keep that. And we don't really delete from strings. We just pick a section that we want to keep. And what I want to keep is beginning at 1 up through the length of the string. Now, I hope some of you are up in arms right now because substring is overloaded, right? I'm using this version where we go inclusive, exclusive on our parameters, but it's overloaded so that I can just provide one index. So what we're going to do is that we're going to keep everything beginning at index 1 going through the rest of the string. I'm effectively chopping off the very first character, right? I wanted to get rid of it because we just considered it. If I'm still here in the method, it means that we have characters to consider. We looked at the first character and it's not an X. I basically just want to keep going. I want to make my string smaller. So we're going to just simply return effectively 0 plus countX, right? Keeping our call going just like before. I considered the first character. It's not an X. I want to keep going because there may be more X's, but the first character has already been considered. So we're effectively adding 0 and chopping off the first character. Now, again, as we've seen from previous coding bats, we don't have to put the 0 plus there. We can just roll with this. I think we should trace this. Let's take one of their examples. Right, let's take this guy here. So let's say I want to count quotes, no quotes. I want to count how many times X occurs in this. Okay, well, let's step inside of this call. First thing I'm going to ask, is the string length 0? No, it's not. Is the first character, the character at index 0, an X? It is. So we're going to put onto the call stack 1 plus, and then we're going to keep going. This method is recursive. It's going to call itself. We're going to pass in a substring, right? C. We're keeping everything beginning at index 1 going through the rest of the string. Okay, I don't quite know what this is, so we're going to step in. We're going to ask, is the first character, well, is the length 0? No. Is the first character an X? It's not. So we hit this this recursive call where we're going to call our method chopping off the first character. We're going to ask, is our string length 0? It's not. Is the first character an X? It's not. So we'll put another call onto the stack where we chop off the first character. We're going to ask, is our string length 0? Nope. Is the first character an X? Yes. Okay. We're going to put onto the call stack 1 plus chopping off the first character. Is our string length 0? No. Is the first character an X? No. Is our string length 0? No. First character an X? Nope. Is our string length 0? Is our string length 0? No. Is the first character an X? Yes. Maybe it's a little too much on the indents. So when I do this last substring, it's going to get rid of effectively the first character. So what we're passing is an empty string, and we would ask, is the first character, I'm sorry, is the length 0? It is, so we're going to get back a 0. So the value that I get from this recursive call is 0. The value I get from this one is just simply 1, which means that this is still just 1, which means that this is still 1. And now this one is going to give me 2. This is still just 2. This is 2. Ultimately, 3. Sweet. Very similar. countHi, except instead of just looking for one character, what we're looking for is a 2-character string. Okay? Very similar base case. We're going to basically consider 2 characters at a time, kinda. and we're going to chop off characters. Eventually, our string is going to have nothing in it. So if our length hits 0, we're going to return 0. Okay. In this case, I'm looking for a substring. We can't use char out here. It's just not going to happen. We have to use substring in order to get these two things. I mean, I guess we could use char out and look for an H, and look at the next one and see if it's an I. And I don't like that. Okay, so if similar situation, it seems to be cleaner to get the characters at the beginning of the string. So I'm going to get the first two characters of the substring. Okay, and I want to know, is that exactly hi? Notice here, we're working with strings, right? Substring returns a string. I'm going to ask, is that equal to a string literal? I'm comparing string to string, two objects. We're using the equals method. If that is hi, I've found an occurrence of hi, we're going to count it. So in this case, I'm going to return 1 plus, and we're going to keep going. In this case, I just considered two characters. I can chop off two characters. So I'm going to call countHi. We need to pass in our string, but in this case, I'm going to get rid of the two characters. Hopefully some of you are seeing some problems that are about to come up. We'll take our string, we'll do a substring of it beginning at index 2. Okay? If I'm still in the method, that means that I'll check the first two characters. They ain't hi. Now, I don't want to chop off two characters because just because the first two characters is not hi, like maybe it's something like this, right? I would ask, is the first two characters hi? Well, no. If I were to then chop off two characters, I missed a hi. Okay, so here I want to put a recursive call into the stack, but I only want to get rid of one character. There's going to be some problems here. Uh-oh. Why? I'm getting string index out of bounds. These aren't stack overflows, so that's important to note, but I am going out of bounds. Why? Our first if statement, if the length is equal to 0. Oh, I could see how this could help us, right? Because I'm going to keep going until I have a string with a length of 0. But that means that a string with a length of 1 is possible. It's possible that that exists in my recursive call stack. Yet what I'm trying to do is get a substring with a length of 2. So we can actually stop once our length is 1. The reason being, if I have a string with a length of 1, it can't possibly contain hi. So why keep going? I think that may be enough. Help me out. Still probably here. Less than or equals to 1? Ooh, that is a possibility. Ooh, good call. Good call. It's possible that we go straight from a string length of 2 to 0 by doing this. So checking for exactly 1 was a problem because we jumped straight from 2 to 0, skipping right over the 1. Good call. Sweet. I think I have, let's see what I have. We just did countX, countHi, multiple choice question. Here we have a recursive method. It's calling itself, and I want to know how many calls will be made, including the original, if we do foo 6. Okay, I'm going to leave that up. Put on a 3-minute timer because this one, you might want some paper for this. And find some monster cat, question mark.
to make themselves smaller.
Ooh.
We say to girls,
No, I'm just kidding. So our answer here is D. So let's take a look at this. It's a bit harder than some of the recursive traces that we've done recently because we got like calls happening in conjunction. This is similar to Fibonacci, and because of that, I'm gonna bring up MS Paint and we're gonna do our best Salcon impression. Where'd it go? Not Diablo. Not that either. Come back to me. So, our initial call is foo. Oh, let's back that up. Let's get a thick boy in here. Foo 6. Okay, I'm going to ask, is n equal to 1 or 2? It is not. We're going to jump down to this recursive call, which puts a foo of 5 minus a foo of 4. And then I need to step inside of these calls. We're going to ask, it doesn't matter which one you pick, by the way, because they basically are going to stack up and then kind of collapse collectively. So we're going to step inside this call. We're going to ask, is n 1 or 2? It is not. So we're going to put onto the stack foo of 4 minus foo of 3. Okay, that's what this foo of 5 is doing. Over here, this foo of 4, I can step inside that one, or I can come over here. Yeah, so foo of 4 is going to, we're going to ask, is n equal to 1 or 2? Nope. So we're going to put onto the stack foo of 3 minus foo of 2. I need to step inside these. Well, we just saw foo of 4, so I can actually go ahead and write that one out. I know it's going to be foo of 3 minus foo of 2. Let's back that up. That was a little horrific. Foo of 2. Okay. I can step inside any of these foo of 3 calls or even the foo of 2. So foo of 3, why don't we do it over here? I'm going to ask, is n equal to 1 or 2? It is not, so we put onto the stack foo of 2 minus foo of 1. Okay, and let's step inside this foo of 2. We would ask, is it 1 or 2? It is. So I'm going to return 2 times n. Now, the value here doesn't really matter as much, but 2 times n in this case is 2, so we're looking at, this is going to return a 4. I can step inside this call, and we would ask, is n equal to 1 or 2? It is. I'm going to return 2 times n, or just simply 2. Okay, I'm solving the whole thing. All we actually care about is how many calls are on the stack. Right? I've got this f of 3 over here that I actually need to finish in this f of 3, which is why I haven't counted those. But I'm just showing that these are coming to a conclusion. This foo of 2 is going to give me 4. This foo of 2 is going to give me 4. Okay, so this f of 3 over here, that's going to put these 2 calls on the stack, right? f2 minus f1. f2 minus, oh, that's bad. f2 minus f of 1. All right, we can solve those, like f of 2 is a 4, f of 1 is a 2. This f of 3 is going to put 2 calls onto the stack. F of 2 minus f of 1. And I can solve those. This is a 4, and this is a 2. All right, the solution here isn't what's actually important. What we care about is number of calls, and I think I can count them at this point. 1, 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so this is the height of the call stack. In total, these calls are what we're actually counting, and there's 15 of those, including this one. Now, we can come through and solve it. I'm not really super interested in that. What we wanted to know is how many calls are on the stack, and you will see some questions like this. Yeah, it's not actually asking for the value. It's how many calls are made. And you can see questions like this. Sometimes they're asking for what is produced, what is returned, what is printed, that sort of thing. Sometimes they're asking how many calls are actually made. And you basically have to be able to do this recursive call stack. So I'm going to give you a coding bat, and tomorrow we'll probably look at doing some IntelliJ. So make sure that you get that set up. I saw that a lot of people already are prepared. They have IntelliJ installed along with the JDK. Don't forget that. Let me know in chat, do you need me to do some type of video on how to install IntelliJ, how to get a hold of the JDK and set those up? Otherwise, I mean, if people want that, maybe we'll record that separately. There is a Canvas guide. Of note, the process of getting a JDK has been updated. Oracle's basically requiring a login now. They want to sell your data. I don't know. That's going to wrap us up for today. I'll see you tomorrow. Let's chill.